Hello class, in this video I'll be introducing the fundamental theorem of calculus. Let's begin. In sections 15.1 and 15.2, you learned how to evaluate an indefinite integral. The result was a function whose derivative was the function inside the indefinite integral. For instance, I will highlight the indefinite integral in purple and the solution in blue. And I ask, why is this statement true? Well, it's true because if capital F of x is equal to the function highlighted in blue and lowercase f of x is equal to the function highlighted in purple, then the derivative of capital F of x is equal to lowercase f of x. And that is what you learned in sections 15.1 and 15.2. We will now introduce the definite integral, which looks something like this. And as I was boxing the definite integral, you may have noticed the subtle difference between the two. What is the difference between the definite integral and the indefinite integral? And if you noticed these two limits of integration, you would be correct. That is the difference between the definite integral and the indefinite integral. And before I get into what these limit of integrations do, let's talk about what the solution looks like. What does the solution to a definite integral look like? And how do you find the solution? The solution to a definite integral with real number limits of integration is a real number, not a function. The solution can be found by applying the fundamental theorem of calculus. And with that, let's introduce the fundamental theorem of calculus. Here it is. It says, let lowercase f be a continuous function on the closed interval a to b, and let capital F be any antiderivative of f. Then this statement that I'm going to highlight in green is true. And what does this mean in words? In words, if we can find an antiderivative for the function lowercase f of x, then we can evaluate the definite integral by evaluating the antiderivative at the endpoints of the interval and subtracting the result. All right, so let's take a look at an example. What is the value of the definite integral? And what does that value represent? All right, so what I'm going to do is I'm going to label lowercase f of x as x squared minus 2x. An antiderivative of that function is x cubed divided by 3 minus x squared plus c. So if I want to evaluate the definite integral from 0 to 3, this would equal the antiderivative evaluated at the two limits of integration, and then we're going to subtract the results. Okay, so capital F of 3 is equal to 0 plus c, and we can get that from Decimus, and capital F of 0 is also equal to 0 plus c. So the definite integral is equal to 0 plus 3, not 3, sorry, 0 plus c minus 0 plus c, which is equal to c minus c, which is equal to 0. So this definite integral is equal to 0. Okay, so now that we have the value, what does this value represent? So I have a graph here, and the limits of integration go from 0 to 3. So what I'm going to do is I'm going to place a coordinate at 0, 0, and another coordinate here at x is equal to 3. So here, this is x is equal to 0, and that is x is equal to 3. Then I'm going to shade the area between the curve and the x-axis. And since the curve is below the x-axis, I'm going to shade it in red. And I'm also going to do the same thing between the curve and the x-axis. I'm going to shade this in green because the curve is above the x-axis. So in green, the graph is above the x-axis, which means the area is positive. Red, the graph is below the x-axis. The area is negative. All right, so what does the 0 represent? Well, if we were to take the area in green plus the area in red is equal to 0. So the area in green plus the area in red is equal to 0. And that is what the definite integral evaluates. And we are done.